So let's try some simple proofs using sets. So remember, definitions are the whole of mathematics. All else is commentary. So let's recall some definitions. We have our definition of a set, and our definition of set equality, and our definition of subset. And we'll have other definitions, but these are a good place to start. So let's try to prove if A equals B, then A is a subset of B. So remember, this is a conditional, and you can always assume the antecedent of a conditional. And also keep in mind that the last line of the proof is what you've actually proven. So we'll start with our antecedent, and so we can assume that A is equal to B. And mathematicians like to say things like, suppose A equals B. And we want to conclude that A is a subset. So let's end there. Consequently, A is a subset of B. So let's pull in some definitions. Now here we're talking about the subset, so we probably want to pull in the definition of subset. And let's see, A is a subset of B if every element of A is an element. Okay, so we want to show that every element of A is also an element of B. And so let's also suppose that we have some element of A. So we know that A is equal to B, so let's go ahead and pull in that definition. And since A is equal to B, then by definition, any element of A is an element of B. And so that means X is an element of B. And so putting our two things together, any element of A is also an element of B, and that completes our proof because that's what's required for the definition of a subset. We can also consider operations on sets. So given a set or two sets, we could talk about the complement, the intersection, and the union. So let's prove, for example, A intersect B is a subset of B. So it's not clear because this isn't written as a conditional what we can start with, but we do know we want to end with the conclusion that A intersect B is a subset of B. So this talks about the subset relationship, so let's remind ourselves what that definition is, and note that we can conclude that A intersect B is a subset if we can show that every element of A intersect B is an element of B. And that gives us a starting point, so let's start with an element of A intersect B. Well, now we have an element of an intersection. Our definition of intersection tells us that if X is in the intersection, then X is in A and X is also in B, which means that X is in B, which provides a link to the last step. Or we could take another example. So again, this is a conditional. We can always assume the antecedent. So let's go ahead and suppose that A is a subset of B and B is a subset of C. The last line that we write is what we actually proved, and so we want to make sure that our last line is A is a subset of C. So again, subset. In order for us to have that subset relationship, we want to make sure that every element of A is also in C. So let's start with an element of A. And where we'd like to get to is we want to show that X in A means that X is in C. Well, we still have a gap there, and we do know that A is a subset of B. So by our definition of subset, we know that since A is a subset, then anything that's in A is also in B. So X is in B. But again, we know that B is a subset of C. So since B is a subset, then anything in B is also in C. And so X is also in C. And that completes our proof.